Let's now look at how we find this Jacobian matrix and what sort of a matrix it is. First of all, what size would we expect the Jacobian matrix to be? To figure that out, let's look back at what we expanded each of these vectors, chi and q dot, to be. Chi was a 6x1 vector of the velocities of the end effector. Q dot had n rows, where n is the number of joints that our robot has, and it has one column. So our Jacobian matrix has to end up having 6 rows and n columns. It has to be a 6 by n matrix where n is the number of joints. So where can we get these 6 rows from? The Jacobian matrix has 2 parts to it. There is a Jacobian linear velocity part on the top and a Jacobian angular velocity part on the bottom. So we would expect to have 3 rows of the linear velocity Jacobian part and 3 rows of the angular velocity Jacobian part. Let's start out by looking at the angular part of the Jacobian matrix. The angular part of the Jacobian is easiest if the joint is prismatic. If the joint is prismatic, then there is no rotation of the one frame relative to the one before it. And so the angular part of the Jacobian is simply 0, 0, 0. If our robot manipulator was a Cartesian manipulator, in that case it has 3 joints, and all of those joints are prismatic. So the rotational part of the Jacobian matrix would have 3 columns, all zeros, because it has 3 joints that are all prismatic. So now, what about the case of a Revolute joint? In writing the Jacobian rotational part for a Revolute joint, we are helped a little bit by the fact that we've used a convention in drawing our kinematic diagram where the rotation always occurs around the z-axis. Because rotation always occurs around the z-axis, we can find the rotational Jacobian part by taking the rotation matrix, which we already know how to find, from joint 0 to joint I, and multiplying that times the vector 0, 0, 1. In other words, we're only going to use the last column of the rotation matrix. We're only looking at the rotation that occurs around z. The first column of the angular velocity part of the Jacobian for a Revolute joint is always very easy because the rotation matrix from frame 0 to frame 0 is just the identity matrix. So the first column of j omega, if the first joint is Revolute, will be 0, 0, 1. For the next column, we have to look at what the rotation matrix is from frame 0 to frame 1. For example, if we were doing this for the spherical manipulator, which looks as shown here, I'm looking at the kinematic summary document that you also have access to on Blackboard. I can look then at A1 from the forward kinematics, and this first 3x3 matrix is the rotation matrix from frame 0 to frame 1. All I have to do is pull out the last column of this rotation matrix, and that gives me the next column of my Jacobian. If my next joint was also revolute, I would go and get the rotation matrix from 0 to 2. In other words, I would have to multiply A1 times A2 in my forward kinematics and take the last column of that matrix. If my next joint was prismatic, I would put in 0, 0, 0, as we learned in the last example. Remember that I'm supposed to have a number of columns equal to the number of joints. So the example that I've shown here is the correct rotational velocity Jacobian part for a manipulator that has 3 joints, where the first one is revolute, the second is revolute, and the third is prismatic.